Okay, so because today is closely related to what we talked about yesterday and the day before, just one other quick little playful 8.1 question. So birth weights for 20 randomly selected American babies. Now let's think about that on the bigger picture. Are kids' birth weights, would you say those are normally distributed or not? Not sure, we're not sure, but what would you think? Would you have a whole bunch of kids that are born around the same weight in the middle and then less and less that are smaller and kind of smaller on this end and bigger on this end? Is that what would happen with kids' weights? I think it is. If that's the case, is it okay to just have a sample of 20? Will these average sample mean, so this is the sample mean, that's what X bar means. And notice on the bottom of your note sheet, I kind of reminded you of every symbol that you need for what we've been talking about. And that list is getting kind of huge. But the sample mean of this particular group of 20 is 7.63 pounds. And so what we're saying is, this is not the actual average. This is not the population mean for the weight of all babies, American babies. Notice there's no distinction here between boys and girls. That is not the average, but that's a sample of 20. 20 is not a very big sample size. What we said the last couple of days is that's one sample size, but then if I take another one and another one and another one, and this is what Taylor was alluding to, and another one and another one, then and started kind of graphing and keeping track of those, the distribution of all these different sample means that I get will actually be normally distributed. And we said that is not going to happen necessarily unless you sample 30, unless you make your sample size 30, unless the underlying population is actually normally distributed. And I think babies probably would be normally distributed, which means a sample of 20 is actually okay. Did you take that away from this last section? Again, the main point is there's one sample of 20 babies. Again, notice the mean is 7.63, the sample mean, I should say. And then I hit another study and notice in this particular group, notice the sample mean, the sample mean or the sample weight went way up, and notice there weren't any kids, there weren't anybody below 6 pounds. There was sort of a whole bunch of them that were between 7 and 8 pounds. A totally different answer. Does that make sense? And that's the big important thing. That's the only important thing you actually need to know for next week for this confidence interval idea. If I take a sample of 20 kids, I'm going to get one answer. If I take another sample, I'm going to get a totally different answer. 7.78, I did it again, I got 7.69. And then I got kind of a big one, right? 8.14, that's kind of a large one. That particular group of 20 had, what did it have? 5 kids over 9 pounds. So that's kind of what made that mean so high. So all we're going to do today is just look at data that is not numerical. You should say that, yeah, 8.14, you're looking at baby weights. That would be continuous data, certainly numerical, but that's continuous data, continuous numerical data, because decimals are going to happen. All we're going to do today is look at percents as data, and that's the only difference. For instance, your screen sharing is paused. What does that mean? For instance, I'll ask you just an interesting question right now. And again, this might pertain to how you think about the project. What are we looking at today? Not the distribution of the sample means, but the distribution of sample proportions. In other words, the data is going to be a decimal this time. So actually, I want to ask you this an interesting question, and this never works very well, because when you ask people in a room to kind of raise their hand about something, there's always like 30% of people that are nothing, that didn't raise their hand at all. But just out of interest, I'll tell you a question I find kind of interesting is what percent of people believe in spanking, for instance, spanking your kids? And that's an interesting one, I think, because people are kind of passionate about it. There's sort of a side that says, I don't want to teach my kids, violence or hitting, and I think there's some other way that I can, train them to do the right thing and smack them. It sounds kind of violent, sounds kind of weird. Other people are like, no, that's actually important. You got to do it correctly. You can't hit them over the head with a broom or something. But if you do it in kind of a controlled way, so I don't think I'll ask you because I'm not going to get good data. So as I said, people tend to not want to answer. But the other question I could ask is, were you spanked as a kid and so forth? But anyway, that's an interesting one. That's the kind of thing that I would think. Yeah. But in terms of a final project, to me, that's an example of a good question. The ultimate question would be, should kids be spanked? And of course, there'd be a whole side of this where you look at literature and all that, which I don't want you to do for your project, but just to go collect data and see, like, has that changed? What have people done in the past? Interesting, just because I brought this up, this is a little bit old. But let's see. And of course, this article had to do with spanking kids in school, because I was talking to somebody this weekend when we went down the Lower Road, and we were talking about elementary school and how the principal used to have a paddle, and it was like that kept a ton of us in line when I was a kid, because it's like nobody wants to go see the principal and get paddled, both because it hurts and because it's embarrassing. So there's like in school, but then there's also just at home. But this is interesting because it says, and I guess the reason I'm showing you this instead of just talking about it is I'm showing you what statistics looks like in the real world. This is a news article from ABC. I mean, this is just people asking an interesting question. And so this says, based on, and can you appreciate this study here? This says, at home, among parents with minor children, whatever that means, 50% report they sometimes spank their child, where 45% do not. Where'd the other 5% go? I don't know. Says it hasn't changed for a decade. It also said, this is kind of interesting, there's a big regional difference in spanking. Southerners, 62% spank their kids, but that's only 41% for the rest of the country. But again, can you appreciate like how difficult it would be to collect that kind of data? And again, what I do, if I was you for a project and I found this interesting, I would just put that out on Facebook as a question, and that'd be my data, like whatever people said. But in the end, that data, I guess, in reference to what this is saying, is probably coming from people that are around here, maybe. And so I wouldn't even have thought to think that, Southerners had a different take on that than other people. But again, the fascinating thing is, can you ever know the answer to the question, what percent of Americans, believe in spanking or spank their kids? And of course, there's a lot, as I said, there's a lot of levels to that. That's what's so weird about statistics is, like, what does it actually mean to spank somebody? That means, correct them by hitting them with something. You get mad and just throw something at them. Does that count? Or does that have to be like some controlled, loving, corrective event? Like, you don't want them to not do well in life, and there's things that don't work, and so you want to teach them not to do those things. But my point is it's hard to collect data, and I wonder when I read something like this, and this is what I hope changes you a little bit from taking this class, is when you read articles like that, I find myself thinking, how did they get that? And they never tell you in an article like this, but they would if it was some kind of a psychological journal, Because how many people did they ask? It says among parents with minor children, 50% report they sometimes spank their child. Did they ask 10 people and 5 of them said yes? Because that would mean, like, please don't write this article because I actually am believing what you're saying here. It's ABC News and I'm thinking this must be true. You see what I'm saying? And for that reason, if that's not reported, that's what people mean when they say statistics can lie, because the sample size is really huge here. Did you ask 10 people and now you're going to tell us all this stuff, or did you do some huge study that was all over the country and there were thousands and thousands of people that reported on it? One of the other, just on a side note, one of the other difficulties with statistics like that is there's usually some kind of a survey, and there's a certain type of person that responds to a survey. Does that make sense? Are you one of those? I'm not. I've never really ever respond to stuff like that. So, like, you know, a person that doesn't respond, is that going to screw up the data? You know, very well maybe. But that's kind of what I mean as far as the project. You know, come up with an interesting question like this. And I want you to think about it, you know, now, so you have time to come up with something that you genuinely think is interesting. But the point here is, notice all of the data is percentages, as it should be. Saying something like 12.2 parents spank their kids, like, what is that? The data here is entirely percentages, whereas on Monday it was entirely, well, a number that we would take the mean of. So just exactly as like what we did last time, of course, if I go ask people a question, I'm going to get a certain percentage. But what do we call that? So in 8.1, we said that was the sample mean. And as I've tried to pound into you, that's wrong. Like, that's not the correct answer for the whole world. That's just the mean of some sample that you took. Whereas the population mean, we have a different symbol for that. But in 8.2, what's the sample proportion? Again, the important word there, well, they're probably both important, but the important word here is sample. Do you see that symbol on your note sheet? It's something we haven't seen before. It's on the bottom of your note sheet. So we are using P for proportion, which we've used before when we did binomial probability distributions. P was our proportion or a percent or a probability. It's the same thing here, but it's a P with a little hat over the top of it. And again, what that means is that's a sample I took. If I did a good job, then that might be pretty close to the actual real percent of American parents that spank their children or whatever. But if I did a terrible job, it could be off by a mile. Or if I got unlucky. This is why I made those Excel models. There were unlucky ones where they bounced way off to the side, and I'll show you some more of those today. So there's a sample proportion, but there's also the population proportion, which is actually just a P. So this is really like your best guess. And the important thing to know right now is that that's all you're ever going to have is a best guess. Unless we limited the population to just this room. And then we decided, you know, what percent of people spank. But, you know, if it's countrywide, then you're never going to actually know. This is your best guess. This is actually the kind of like the right answer. So P for proportion. This guy right here is actually pronounced P hat, which is kind of weird. That's how you say that, P hat. A little bit weird. Looks like fat. I know. PH. I actually thought about that today. Fat. I think it's fat. Keep in mind, like, think about this practically though. Some of you are still struggle with percents, and this is a place that might hurt you. But it's like, how would you ever get that? How would a person discover the percent of people that spank their kids? You can't collect the percentage. Do you understand that? What do you have to do? Well, you'd have to go ask, I don't know, 157 people. So I go do my sample of 157 people, and that'd be a good sample size. That's quite a few people. So I got my sample of 157 people. Maybe that's all my Facebook friends. And I say, do you believe in spanking? Yes or no. And by the way, if you want a good data for that project, if that's the route you go, you got to be really careful how to ask that question so that you get the answer you want. Like make them say yes or no. Don't say what's your opinion of spanking, because then you're going to get this weird spectrum and it's going to be hard to determine. Keep in mind a percentage ends up kind of like binomial. It's either yes or no to some question that you're asking. And the variable then would be, you know, do they believe in something or not believe in something? So let's say, since we've been sticking with spanking idea, that I don't know, 84 believe in spanking, at least in theory. And so does it make sense then? You're going to have to take 84 divided by 157, in other words, x divided by n, in order to get p hat, which, as you know, there's more than one way I can write that down. I can just say it like it is, 0.535, or I could write 53.5%. As I've said also, because we're doing a lot of math with this stuff, it's probably better. Although in an article, you may have noticed in that article, they never said 0.535. They always say percents. They say 18.6% or 19%. I'm just going to leave this as the decimal that it is. I mean, the point is that's how you get a probability or a percentage or a proportion. You got to actually collect some numbers. Let's see. I think maybe I'll tell you this right now. No, I'm going to tell you that in a minute. Okay, so let's go take a look at another visual for this. Let's see, share that screen, share. Let's do dice first. So let's stare at this for a second. So this is somebody that is going to take 30 dice and just throw them out all on the table at once. And what we're going to look at here, as I said in that chart over there, is just the probability of rolling a 5. Now, you know that you don't have to do a study to know the answer to this question, because this is not like people in spankings. That's like an opinion. You can't arrive at that. You can't arrive at that any other way than experimentally. But in the case of a dice, you can actually arrive at the answer to this mathematically. Since there's 1 5 on a dice with 6 sides, the probability of rolling a 5 is 1 out of 5. So, I'm sorry, 1 out of 6. So what's your calculator say 1 divided by 6 is? Probability is ways to win divided by ways to play. There's only 1 5 out of 6 faces. So have that in your mind. And what you should see is exactly what I said up here. Notice I said P. The population percentage is 0.1667. I rounded that off to 4 decimal places accurately. That's actually the probability, the actual probability. And however, is that what would happen? Let's see, 1 out of 6. If you rolled 5 dice then, I'm sorry, 30 dice, 1 out of 6 of them would be a 5. So that'd be 5 5s. You'd expect to get 5 5s. But is that what's going, this is the point. Is that what's going to happen when you roll those dice? Are you going to get 5 5s every single time? Is it going to be 16% every single time? That's how many 5s you get? No, there's variability to that. That's the main idea. It's the same idea from 8.1. Even if the real answer is 1/6, are you going to get 1/6 when you roll them? You're not. Did we get 1/6 on this particular roll? And notice, again, this is just kind of neat for you to see, but what did I do to mimic rolling dice? I said ran between 1 to 6. So this was a 3, that was a 6, that was a 4, then a 6 and a 2 and a 6, and you know, all the way down, there's a big list. There's 30 dice down there. And I didn't show you the, you know, kind of what's behind the scenes here. I didn't show you these frequencies. Maybe I will show you that really quick. So notice what happened on the second roll. Something really surprising just happened on the second roll. Do you see what just happened? I rolled 30 dice. The expected value, the mean from a previous section, the mean is n times p, which for us would be 30 dice times the probability of 1/6, which is 5. The mean, the number you would expect to get would be 5. But as I said, it's not going to be 5 all the time. It's going to bounce around. How many did we get on this roll? We got 0 of them. Does that feel pretty unlikely? That feels really unlikely to me. You're going to get none. But again, that's the idea behind the way statistics work. Or when you perform a study, your sample could be really wrong. If these dice were not mathematically able to be arrived at, and I just went and did a study and I said, hey, what's the probability of rolling a 5? There's 30 dice out there in a sample of 30. I asked 30 people, do you spank? And everybody said no. And then I went forward and said, okay, world, 0 people, 0% of people believe in spanking. The point is, from this section, you might be wrong. And in this case, because we know the math is 1/6 and that we would expect to get 5, that's really surprising. Now, again, you understand the concept of mean and standard deviation. If I take the mean and I add or subtract 2 standard deviations, we said this is what's normal. Inside this range is normal. So right now, I'm actually kind of curious, was that abnormal, or is that going to happen again? We actually got no 5s on that particular roll. Well, let's do some more. Notice on that one, what happened on that one? What's p hat? It's exactly what it should be. In a sense, that's not surprising. I mean, if the probability is 1/5 and then you were to take a guess as to what's going to happen, I'm sorry, 1/6. If it's 1/6, then you were to take a guess on what's going to happen, you would guess 1/6. So that performed as it should have. What happened on the next one? Notice I got 0.1. And then another 1/6. Again, not surprising that it's winning, if you will. The point is, if I go do a sample, it's going to bounce all over the place. Are you feeling that? This is no different than what we did the other day. But if I take a sample, it's going to bounce around everywhere. Now, if I just let this run a little, again, I'll stop right here. Oh, look, there's another one that was exactly the right size. It was the percentage we predicted. We predicted 0.1667 because we mathematically know that is the population proportion. And then we went out and did a sample of 30 people and we got exactly that answer. That's what you'd expect to happen. Notice we haven't gotten any more zeros. And not only that, we didn't even get any of these. And so that's feeling like an outlier, isn't it? Like so far. So they're bouncing all over the place. This is what makes games fun, right? You roll the dice, something interesting happens. Let's let this rip for a while. What do you notice that begins to happen over time? Notice there's a distribution of those sample proportions. We're getting all kinds of different answers. Notice if I stop here, we apparently got one really high one over there. You may recognize that one. That's 0.333. That's 1/3. So usually it'd be 1/6, but we got 1/3. 1/3 of 30 is 10. So on that particular roll, there was 10 5s. That's double the number that you would have expected. And so that, again, that feels like, is that an outlier? Is that to be expected? Is that inside 2 standard deviations? Or is that out there in that little tiny tail that's super unusual? And again, imagine yourself performing a study and you sampled 30 people and the answer you happened to get was 10. I threw the dice and I got 10 5s. And so it's like, oh yeah, the probability is 10 out of 30, that's 1/3. And then that's what you write to US News and tell everybody about spanking, so to speak. That's the one study you did. Is there a chance your study was one of the terrible ones? That's what we're going to talk about in chapter 9. What do you notice about the shape of this distribution? Notice we just had one that was even higher down there. This would probably be helpful if I went in here and turned on the data labels. So you couldn't see this because I make this a little bigger. So we actually rolled those dice, those 30 dice out on the ground 412 times here. What you should not be surprised at is the fact that there's a cluster around 0.1667. However, notice it's not winning, and it's actually not winning by quite a bit. Does that bother you a little bit? It should. Shouldn't this be the tallest one if that's kind of the right answer? Now, remember what this means is, well, we only did 412 trials, and maybe that just randomly happened a little bit. Notice we got 0 another time. We have 2 zeros now, not just one. Or maybe it means the dice are, what's the word for that? Somebody plugged them, and made them put lead on one side so it rolled another. Yeah, weighted. Maybe they're weighted, and maybe we're kind of proving that that's the case here.
Does it have anything to do with that you only have it measured up to 40% because it could be above that?
Good point. Good, very good point. Is it possible to roll 30 dice and have every single one of them be a 5? In other words, 100%?
Or even half?
Or even half, even 15 of them? The answer is, yeah, it is. It is possible. Not very likely, but that's exactly what standard deviation is about. Now, the reason I didn't include those is notice it doesn't seem like getting past 40%. Let's see, what is 40% of 30? 12, that's 12, rolling 12 5s. That happened one time. And so is it possible to get more than that? Yeah, but not very likely. So that's 412 trials. Let me flip over here to 8,748 trials. And again, let me turn on the data labels. Thought I saved that with 8,000 trials on it, but obviously I did not. Is this one reading from that one somehow? Let me fix this really quick. Actually, I'll tell you what I'm doing. What this is doing is actually reading its data from the other page. Does that make sense? I copied it over here. So I'm going to click on this. Let's see, I got to go over here. See where it's reading its data from these two cells right here on this page. I got to do the same thing over here. This one is select data. See how it's reading it from that page over there? I want to read it from this page over here. There, I think I fixed it. What do you notice when I let this go out further? As Garrett said, notice there's actually 10 of these that were at 40%. Does it feel like there actually could have been one past this? And maybe I should have shown that on the graph. I'd say yeah. Remember, that's what the idea behind a normal distribution is. It actually goes forever. There is a chance of rolling all 30 dice to be fives. It's just a 0 plus kind of a chance based on what you understand. We'll talk about that in a second. This is kind of a tricky question here, but do you notice that's normal-ish, but it's actually not normal? Is that a little skewed? Do you see that? That actually is a little bit skewed. It's a little bit skewed, well, to the right, because this tail to the right is a little bit longer. The other thing I find amazing is notice how many times we actually rolled no fives, even though we would have expected 5 fives. That's surprising to me how small that is. Notice you can't go less than that. Does it make sense if I went long enough, this bar would be really tall and there is not going to be any negative percentages over here? That's another reason why this is actually not perfectly normal. So for that whole percentage thing that we do, like normal CDF on our calculator and inverse normal, that's entirely based off the distribution being normal. This is reasonably close, but it's not normal. Whereas when I rolled 20 dice, watch this. Better save that. What do you notice about that when I rolled 20 dice? You see how it looks normal now? And again, I saved it with 5,000 trials on it. I just stuck a stapler on there and let it go while I was doing something else. Notice that looks normal now, which kind of means we could use normal CDF, like some of those calculations now. We can say that 2.5% are out in the two tails, outside of 2 standard deviations. Like, what's the deal? How come 30's not normal, but 120 is normal? Secondly, on this, notice that just like we said last time, isn't the middle of this normal distribution, isn't that showing us what we already mathematically knew, which is the mean is 0.1667? If you let it run long enough, that will be the highest point. So the main idea in chapter 9 that we're going in a couple of days, I need to give you a break in a second, is to say, Well, there's 5,187 different studies that a person might have done. And again, that doesn't mean people do that. It's just that if you did a study, which one of those are you? I mean, it'd be great, as I said, if you did your study and you found this, but how do you know this wasn't yours? How do you know that wasn't the unlucky one that you happened to do? Does that make sense? That's what we've got to talk about. Notice there were 4 studies over there. And also notice these bars are so, there's not even, the labels can't fit on here. Does that make sense? There's so many bars that there's not enough room to fit all the labels. So I don't know what that is out there. Is that? But, what if that was your study? And then it's very different to say that, oh yeah, the probability of rolling a 5 is actually 25%. 1 out of 4 instead of 1 out of 6. So this is cool to see because we actually know the correct answer because it's mathematically possible to figure out the probability here. So we actually know the population proportion is 1/6. And so then when we watch a sample being taken, we see that no, the sample means bounce all over the place and create a normal distribution. Okay, so let me draw one conclusion from that you need to understand. And I think this is on your note sheet. And that is this: for the distribution of, again, sample means to be normal. Again, what we just saw a second ago was it didn't work at 30, right? It didn't work at 30. What's the rule of thumb that nerdy statisticians have come up with? I want to see if I actually did put this on your note sheet somewhere. I did. Can't zoom in. The shape of the distribution of p hat is normal if, look at that statement right there. It's hard to see on mine because I can't zoom in, but if NPQ is greater than or equal to 10. I'll write that so you can see it. If N times P times Q is greater than or equal to 10. So for the dice, let's see. So for the first example, when N was 30, N was 30. The probability that we were interested in was 1/6 because we were saying rolling 5s. I'm going to write 1/6 or 0.1667. What was Q again? Sorry for the. What's Q? Yeah, it's like the opposite or the complement to that. In other words, if you have a 1 in 6 chance of rolling a 5, then automatically you have a 5 in 6 chance of not rolling a 5. Notice you're making that binomial. You're making only 2 choices out of that, even though a dice has 6 choices. You made a game up where you're interested in 5s or not 5s. So this would be 5 out of 6. How is that arrived at? 1 minus 0.1667. So that could also be, what is that, 0.8333? So you can type either one of those. Well, what is that? What is 3? I'll type the decimal version of it. What is 30 times 0.1667 times 0.8333? Oh, it's like 4.2. So did that meet the requirement? Can you appreciate somebody maybe did something like what I just did? Notice that 30 trial actually wasn't, it was going that direction, but it wasn't perfectly normal. That's not bigger than 10. So I guess if I was collecting dice and so forth and trying to make an inference from this, I'd have to roll more than 30 of them to kind of do what we've been doing. What about n equals 120? Well, that'd be 120 times 1/6 times 5/6. I'll type it in that way this time. 120 times 1/6 times 5/6. Ah, 16.
Where did the 10 come from?
This is from Nerdy Mathematicians.
Oh.
Yeah. So some nerd figured that out. If that expression multiplied out is more than 10, then you'll get a normal looking distribution of the sample means. And again, why that's important, remember, is we can take percentages. We can take percentages from that chart because of kind of the empirical rule in the normal CDF button. We can take percentages based off of that, which is kind of cool. Question. Say again? Let's see, can I zoom in? Trying to share this screen, it isn't, I think it's my camera. I think you're actually seeing my camera rather than this camera. Oh, I know what I can do. Yeah, that's pretty zoomed in. Now, with respect to a test and things, I'm not going to ask you like a trick question. I'm not going to, say you're rolling 30 dice and ask you to figure something out, and then it's going to be like, haha, you're wrong, that isn't normal. But if you are going to use this logic, if you are going to say this is, this pertains to a normal distribution, then you do have to know this. So, Now, to use normal CDF, since that's a normal distribution, what things do we have to type in? We have to type in like a lower limit and an upper limit. What else do we have to type in? A mean. What else? A standard deviation. So that's the interesting part of what we've been talking about is what's the standard deviation? Like you would expect to get 1/6 of your dice to be 5s. But what's the typical deviation from that? What's the standard deviation? If we don't know that, then it's kind of hard for us to look at that dice thing a while ago and say, is that really weird that we got 50% 5s? Is that strange? Do you see why standard deviation is so important or why it's kind of powerful? Well, again, look at your note sheet. Because I'm gonna, what about the good old standard deviation? Notice your note sheet says that the standard deviation of the distribution, does this weird statement make sense to you? Again, mathematicians love this kind of stuff, but people hate it. Normal people hate it. The distribution of sample proportions, that's what we just looked at. We saw that normal distribution of all these random different sample proportions. We did 5,000 samples of rolling 120 dice. What kind of a standard deviation did we get there? Again, I would argue if we looked at the graph, we could probably estimate it. But what's the formula for that on your note sheet? The square root of P times Q divided by N. You may remember before we had one that almost looked like that. It was, except it was the square root of P times Q times N. But the only reason this is divided is because we're trying to get it to a percentage. Because our data is a percentage, then we need our standard deviation to be a percentage. So it's kind of the same formula. Okay, so for the dice, where N was 120, then I would say, okay, then the standard deviation of that distribution that we just looked at would be equal to P, I'll write the decimal version of this, times Q divided by N, which was our sample size of 120 dice. And then I'm going to take the square root of that. Early in this class, I warned you, or we spent a little bit of time next door talking about algebra, because that's a fairly complicated formula, right? The order of operations. Fortunately, I can just type what it says. The square root of 0.1667. Do you agree I'm rounding that off? Because it's actually 0.1666666. Did you see that on your calculator? So, I hope this is accurate enough. So I can just type what it says. Your calculator knows the order of operations, and it actually doesn't screw that up. If you're worried about this giant division sign, you people that are a little better at algebra, and you want to go back and put parentheses around those two things, you can, but it won't change the answer. I'll show you what I mean by that. So I got approximately 0.034. In other words, if you went here and said, I need parentheses around all of that stuff, in a sense, if that was you, I'd say good for you for thinking like that. However, you get the same answer in this case. There's no giant division signs in your calculator, and that makes order of operations kind of a pain sometimes. So I need to shut up after this and give you a little break, but we know that the population proportion mathematically, and even by looking at the center of that distribution of sample proportions, for both reasons, we know this is the population proportion for the percent. And now we know that the standard deviation of that is 0.034. Notice that's entirely based on math. So I could even call this just the standard deviation. So we're going to go back and look at that dice rolling thing in just a second and kind of see. So it's basically saying it wouldn't be weird to be off by 3%. We would expect 0.1667, but if it was different by 3%, totally typical. Let's take a break and then we'll look at that in a little more detail when you get back. Long.
So kind of like a side note, something. Oh, go ahead.
I was just gonna ask how you suggest I access the handbook.
Two.
You told me to redo that,
Oh, okay.
but that's not on there, and I think I gave it to you on paper.
It could be, yeah. I'm just gonna pull it up and print it next door for you. This one, the one with the beams on it? Yeah,
I got a lower score on that because you could decipher my words.
Let me double check.
okay, it's popping out in there right now.
That's just
What concepts are you using?
I read that book. And we talked about it. Like, for example, it's like calculating. Or calculating like before the avalanche. And that's frequency limit or.
Yeah.
I don't totally got it. Just trying to.
So the interesting thing about like the dice thing we were just doing is I made a percentage of this and said, hey, let's look at this from the perspective of percentages. And then, but the other thing we could have done was say, no, we're not concerned about the percentages. We're actually just concerned about the frequency. Like how many fives did we roll? 8, 9, 12, 2. But we're not reporting percentages, we're reporting numbers. Right. So there's a lot of cases in life where like, you can make a percentage out of the data, or you can just leave it as numbers. So the question is, is it the number of snowflakes that it takes for that to fall, or is it the percentage that it takes?
Yeah.
That's actually kind of two ways. Could potentially be two ways of saying the same. Those books are good. I read two of those too. Tipping Point and Outliers.
Yeah, that's.
Hey,
I don't know if I should do that.
Or you could also just.
I did 3 new ones? Yeah.
I think
I mean, you get 3 more tries. Yeah. Well, yeah. For sure. So nervous. Can't imagine. Around. So.
Where do you leave? Let's find the time. One-on-one.
Oh, thank you so much. Yeah, I can actually kind of put it together.
That would be great. I'm gonna write that down.
Yeah.
You have to have like a meeting with.
That's what I said. I'm like, I think it's good.
That's just, that's exactly right. It's basically saying if you know the actual mean height for the tree, the population mean, then that's exactly the same.
Okay. My hand down three.
No, it's on my desk right now, and I was actually making some, but that'll be done today,
Okay.
for
Yeah,
sure.
I really want to cost, but I have 36. So
Yeah, so on Tuesday, let's really like sit down and look at your grade, look at the grade book, and like put scores in there, like what we have to get on the last test, and like is it possible, all that kind of stuff. Let's play with that whole thing, so do everything you can. And as far as, I know, I'm pretty sure I opened up 7.1, 7.2 like for a week or something. It wasn't
Yeah,
just for a day,
yeah.
So also let's look at, so let's start with questions about chapter 7. Try to
because I played it. Yeah, I'm
quick
gonna go
tutorial
find
that
it
works.
and watch those videos.
Okay.
Or start them because it's kind of long.
Yeah, for sure.
And then I'll make note of things.
Yeah, and I was like, it's my
Yeah, perfect. Okay.
Oh, yeah, I was just recording it here, and I saw it here. Yeah.
Okay, let's try to make this practical now. If you haven't looked already, your assignment for this section is teaming. There's like 3 questions, super easy. And that's really what I want to do now is just kind of make sure you can do some real problems with this. So let's do that now. So on this, when we performed this experiment 5,000 times for exactly the calculation we just made, when n is 120, we found the mean and the standard deviation. The mean is 0.1667, just like this distribution shows. Again, that distribution of the sample proportions, they're all over the place, but the strong majority of them, the center of that normal distribution is exactly at the population proportion, just like math would say. Math, we knew the right answer in this case was 0.1667. Sure enough, when we performed this experiment and distributed 5,000 sample proportions, sure enough, the center of that was right where it was supposed to be. But when we stared at this, then we said, yeah, that looks like a normal distribution. But again, what's the standard deviation? Well, I don't know about you, but I think of this, I think of maybe from here to here, like that bar right there. You see I selected that one bar. Maybe right about there is one standard deviation to the right. I'm totally guessing when I say that. And then maybe I'd have to go clear over to here to get the second one. That'd be 2 standard deviations. Well, see, what's cool is that's exactly what we just calculated. So let's take a look at that. So here's what we just said a second ago. I'm actually going to switch this. We just calculated, we knew the population, notice that's P, not P hat. We knew the population proportion, 1/6 are going to be 5s. And now we know the standard deviation, which is really cool. I hope you have to learn nothing right here. You should be good at this now. So if I took the population proportion plus 1 standard deviation, let's see, my calculator says that is 0.1667 plus 0.034. That takes me out to 0.2007, in other words, 20%. And if I take that population proportion and subtract 1 standard deviation, I get 0.1327. My point is we could actually put those on the graph now. So again, I'm just eyeballing this and saying, I don't know, does that look like 68% to you? This is again why it's so important that this actually be a normal distribution, because the middle between 1 standard deviation, between 1 and -1 standard deviations is not 68% unless it's a normal distribution. So that's why that NPQ thing bigger than 10 was important. And so I actually have labels for these. I have locations for them now. So this is 0.2007. This one's 0.1327. So remember, what's powerful about that is that's saying, without using the normal CDF button, that's saying 68% of my trials should land between those 2 values. Does that make sense? I wonder if that actually happened in our little experiment. Could we go out yet 1 more standard deviation? I'll write it differently this time. The mean plus or minus 2 standard deviations. I'm going to write it this way. I got 0.2347 for the high end. And if I take the mean minus 2 standard deviations, I get 0.0987. one of your questions on your assignment? I know it looks something like that. Now that you know this is what's kind of cool. What you should understand is, you know, what's sitting out here is 2.5%. 2.5% of the time, you actually would get something over that according to the empirical rule, right? Without even doing the normal CDF button and stuff. Remember, that's a tiny number, but 0.025, 2.5%. How many trials did I have just a minute? I forgot. It was like 5,187 or something like that. I forget. Notice, although that's a tiny percentage, notice that's actually still a pretty huge number. So if I rolled those dice 5,187 times, although that's a tiny percentage, and we said that's out there in the unusual land, that's beyond 2 standard deviations, that's really unusual. With 5,187 rolls of the dice, that's actually 130 times I would expect to get something that high. That's quite a few. That's a tiny percentage, but it's quite a few. But based on nothing that you don't already know, does it make sense you can answer questions that are a lot more varied than this? In other words, this one's kind of a empirical rule question. Empirical rule meaning you can only be plus or minus 1 or 2 standard deviations. But does it make sense you can answer other questions too? Like, what's the probability that I would be between $10 and 20%? So if I roll the dice out there, what's the probability that I'll get a number of 5s that's either somewhere between 10 and 20%? So from a casino perspective, if this was a game, I'm gonna roll 120 dice. What's the probability that I'll have between 10 and 20% of them will be 5s? Notice the empirical rule won't answer that. The empirical rule only answers it based off of exactly 1 standard deviation. But again, this is a normal distribution. So this is just like in the last section, this is a normal CDF question. I'm asking you for a probability. So if I say normal CDF, let's see, what's it asking for? Lower limit, upper limit, the mean, which was 0.1667, and the standard deviation, which is 0.034. Now, again, I rounded those off, right? So, I mean, this is going to be correct, but might it be wrong in my open math because of some rounding issue a little bit? Yeah. So the point is, if the distribution is normal, then you can make all these cool predictions that aren't just 1 and 2 standard deviations. So I say second distribution, normal CDF, lower limit 0.1, upper limit 0.2, mean 0.1667. If you wanted to get this, no, I won't say that now. And the standard deviation was 0.034. By the way, I don't know if you remember this from what I wrote, but it was 0.0340 was the next number, which is why I don't have a number after this. So I'm just rounding whatever, however it feels to me. So what percent of the time? You know that 68% of the time I'm going to be between 0.1327 and 0.2077. But what about between 0.1 and 0.2? Well, notice this number is almost 0.2, but 0.1 is a little further to the left. So do you agree that between these two, it'd be 68%? So if I go a little to the left, then it's going to be more than 68%. Again, I'm just pushing calculator buttons, but if I get something that isn't more than 68%, then I'm going to think something's wrong. And then, by the way, notice that's 0.0987. That's almost 0.1. So actually, it's almost like the answer is just a hair to the right of this from here all the way to there. So again, if you had that note sheet, it's almost going to be these all added together. I don't remember what was that 13.5%. That's stuck in my head. 13.5 plus 68. That's going to be about what that is. What does it say it is? 81%. So again, your conclusion should be, oh, okay, I'll bet on that. There's an 81% chance that's going to happen. I'm in. I'll bet on that. You answer this one. What's the probability of being below, or what percent of the rolls would be below 5% of fives? Again, we expect 0.1167 is, that's what we expect. So we're way down. I said below, we're way down in this tail over here. We're talking about that teeny little amount over there. We're going to get a really tiny answer for this. Notice from the empirical rule, below 0.0987 is 2.5%. And we're less than that, right? What changes? Based on this picture, my upper limit, you should not be screwing this up anymore. My upper limit is 0.05. My lower limit is some tiny number. I'm going to say -12. Remember, that goes forever. There's no way to get a negative percentage with dice. You might say that the low number is 0. But remember, the distribution actually goes forever. So just to be safe, I'm going to put some big negative number in there. And the mean and standard deviation are unchanged. So what does my machine say that is? 0.0, don't call it 0.5, 0.05. -12. I got 2.99. Except you should say, no, you didn't. Again, a lot of people that don't think much are going to go, oh, 2.99%. But remember, this is popping out a decimal. So again, notice there's an E there that actually says, oh, by the way, the decimal point is actually 4 places to the left of that. So that'd be 1, 2, 3 zeros and then a 299. So rounded to 4 decimal places. So it's actually 0.03%. Don't bet on that. However, if you rolled the dice 5,187 times, notice it actually would predict that's going to happen twice. Isn't that amazing? That's 1.5, which rounds is so somewhere between 1 and 2 times. That's actually going to happen. Just because it's unlikely, just because it's tiny, doesn't mean it's impossible. Is it possible that every single dice is a 5? Yeah, it is. Not very likely, but it's possible. However, if you have roll it 5,000 times, that's actually going to happen. You see, this is the same thing we did in 8.1. It's just that our data is a percentage this time. We have a slightly different formula to calculate standard deviation, but it's the same logic. Andrew.
For finding standard deviation, like for the homework, we're given a percentage and n.
Yep.
So is the formula for the standard deviation on this new sheet the one that we would use?
Yep. That's all we had here. We had n is 120 and we had a percentage of 1/6. The recipe for standard deviation though also calls for Q, but Q is made by going 1 minus P. Let's do another example. And again, I have a visual for this, so I think this will help. Let's do an example with cards. Actually, since this is up, take a look over here. Does this match what we just predicted? I just asked you the probability question. What's the chances of being less than 0.05? Notice we happen to have a number that's reasonably close to that. And although it was unusual, it happened 3 times. You see how powerful this is? We're literally predicting the future. That's what's kind of cool here. This is why casinos can make money for games like this. So here's another cool simulation. I did something like this before. Let's talk about drawing. Actually, I want you to think about this before I even put it up. What's the probability of drawing a face card? What's the percent? If I draw 1 card out of the deck, what's the percent chance that I get a face card? Like that. Who knows? Nice and loud if you have an answer. How many face cards are in the deck? 12. How many cards are in the deck? 52. 12 out of 52. Which calculator say that is? 12 divided by 52.
0.2307.
0.2307. So 0.231. So it's like a 23% chance. Again, just like dice, we can mathematically know the correct answer to this. You see the difference in the study. What percent of people spank their children? We don't know the right answer to that question. All we can do is go perform a study and kind of hope it's accurate. But here we actually know the right answer to the question is 23.1%. So that's kind of interesting. So we drew one hand. And notice this time n is 5. I'm drawing 5 cards and I'm saying, what's the probability of getting a face card? Well, notice you have a 23% chance here, a 23% chance here, a 23% chance here, because I'm drawing 5 cards. As we did over there, if you take that number on your calculator, 0.2307, and you multiply by 5, n times p, then you get a number that's around 1. In other words, you would expect to get 1 face card. That'd be your best guess. I'll get 1 face card. That's what would happen if the mathematical probability is 23%. And notice that's exactly what happened here. You got what you expected. And so you should say, of course. But will there be variation from that? Same question, same concept. Will you get 2 sometimes? Will you get none? Will you get 5? What do you think? Will we ever get 5 face cards, do you think? Again, the answer to that is based on the standard deviation, isn't it? We know that we expect to get 1, but is the standard deviation large enough that I might actually get 5? It sort of feels like yes if I did it 5,000 times, doesn't it? If I drew 5,000 times, but probably if I drew like 6 times, we probably won't get that. Well, let's take a look. Gotta make this a little smaller since you can't see it. Okay, so we drew 1 time, and look at those percentages that are on the bottom. These are your choices. You could get 0 out of 5, which is 0%. You could get 1 out of 5. 1 divided by 5 is 20%. You could get 2 divided by 5, which is 40%. 3 divided by 5, which is 60%, and so forth. Or you could get all of them, all 5 of them. And notice we don't have as many possibilities down here because I only drew 5 cards. N is 5. Now you should already expect that that's not enough, if you will, not enough cards to draw. But okay, fine, let's start drawing cards. So second draw is done. Notice this time you got none. You probably would agree that's not that weird. I mean, it's the standard deviation from 1. Probably it's not that strange that I got 0 on a particular turn. And then I got 2 on this one. I got a king of clubs and a jack of diamonds. That's kind of cool. And then notice I got another one that was a 1, 20%. I got 1 jack. So notice this one does it make sense this is going to be the tallest bar? Because we said the actual mathematical probability was 23%, and isn't that closest to 20%? So this is going to be the tallest bar, and it's already with only 4 cards drawn, only 4 hands played. We're already kind of looking correct. Okay, well, let's let this go a while. Notice we got a whole bunch of 0s. We haven't got any 3s yet. We haven't got 3 face cards yet, but I bet we will at some point. Notice, sure enough, the tallest bar. There's one. We finally got 3 face cards. I don't know about you, but it's starting to feel less likely that we'll ever get all 5 face cards now. Oh, look, we got 4 face cards. 4 out of 5 is 80%. We got that once. But this is only 127 hands drawn. What if I just switch to 8,633 hands drawn? Did we ever get in 8,000 plays of the game? Did we ever one time get all 5 face cards? We didn't. Remember, that's an experiment though. Is there a chance that on the very first time you played the game, all 5 face cards? Yep, that'd probably be a big winner at the casino apparently. Do you agree with that? Seems to not happen very often. Hasn't happened yet in 8,633 turns. What do you notice about the shape of this distribution? Oh, this is like the last one. It's not looking at the right screen. I made copies of this right before class, and let me fix this. Oh. I don't need to edit that, but I do need to edit this. That's better. Notice in 8,633 plays, we did get it 3 times. So even still, that feels like that should be a big prize at the casino, right? Maybe that's the $1,000 prize or something like that. Notice the bar is so small, given how tall this bar is, that you can't even see it yet. This is how tall it is when there's 96 of them, so no wonder I don't see it. But importantly, what do you notice about the shape of this graph right here? it's skewed right. It's not normal. Does that make sense? Remember the NPQ thing being bigger than 10? Calculate that here. Given that you know the probability of success is 0.231, do the NPQ thing on your calculator. Is it more than 10? N is 5. P is 0.23. Again, there's a rounding discussion here, but did you get something like 0.9 when you did that? I took N, which is 5, times P, which is 0.231. That was our probability, our mathematical probability, and that would make Q 0.769. I got 0.9. I didn't even get 1. Like, this is a long ways from being 10, and that's why that's so not normally distributed. Look down here below though. N is 60. Is that enough? Redo your calculation with 60 cards instead of 5. Is this going to be normally distributed? Is it? 10.65, barely. Notice it barely made it. I got 10.65 for that. It barely made it. So let's go take a look at that. Aha. So that's kind of cool. Again, all I want to do is just familiarize you with this particular situation. I want to just ask you some questions again. First of all, notice if you have 60 cards, there's a lot more percentages that are possible. There's actually 60 of them. But notice I didn't even include 0%, because that would mean if you drew 60 cards and you got 0 face cards, that's actually pretty unlikely. But notice the highest one. A second ago, we said 12 divided by 52 was 0.231. Notice that's the tallest one, as you would expect. That's the center. The distribution of the sample proportions matches the mathematical truth that the probability is actually 0.2307. So that's the tallest bar. And notice, because that moved the whole distribution way further over, now it actually looks normal, which means we could use these probability based on the normal distribution kind of questions. We could now answer those. We would not have been able to do that if we only drew 5 cards, but we could do it if you drew 60. Now you might think, how can you draw 60 cards? Because decks only have 52, but remember in casino games, a lot of times they'll play with 6 or 7 decks, so people can't count cards. So you just have to have up to 3 decks. That's not as weird as it sounds. Interesting. If I ever shared that screen. How does that look backwards? So anyway, that's kind of cool. So I just made those calculations. And so basically this one will be normal. And again, what do I mean by normal? I mean the distribution the distribution of the sample proportions will be normal. So therefore, I could ask you questions about that now, just like we did a second ago. So you do this and then we'll be done. 12:30. What time do we get out of here? 1. Yeah, we got time. Could you, number 1, with n equals 60, since we decided that was actually okay. This one was not normal. Could you establish limits for plus and minus 1 standard deviation and plus or minus 2 standard deviations like we did a minute ago? So we just saw that cool normal distribution. 68% were inside 1 standard deviation. Could you establish that? $60. Because we can't do this with 5 because that was not going to be a normal distribution, but we can do it with 60. Discuss this with each other. Like you got to calculate the standard deviation. You have a formula for that. We established earlier that P was 12 divided by 52. Which I'm going to call 0.2308. .1% or 0.2308. And we saw that 60 worked. So powerful. You're establishing the standard deviation that represents the fact that you're not just going to get 23% face cards every single time. There's going to be a distribution. Powerful for predicting the future. What's that distribution going to be? Has to know this ahead of time because it cannot stay in business. Predicting the future here. We know exactly what's going to happen even before it happens. Double check your standard deviation. Did you get what I am getting? I got 0.0544 rounded to 4 decimal places. Did I give you enough time? Center of the distribution will land right at the population proportion, the actual right answer. And although that's what we predict to happen, 23% of the time we'll get face card, there's going to be a normal distribution of scores that are away from that. If I take this plus 0.054, I get 0.2852. If I take that minus that, I get 0.1764. So now I can predict ahead of time as the casino that 68% of the people that play this game are going to get between 17, 18%, and 28%. That's a pretty big standard deviation. 5% is a pretty big standard deviation. If I go 2 standard deviations out, I get up to 0.3396 for this one. And all the way down to 0.122 for that one. And as we've said many times, that would be normal. That's gonna 95.4% of the time we're gonna land in there. One more question. What's the probability then of getting a p hat over 40%? You draw one sample of 60 cards. Notice I call it p hat. You're going to get one sample over 40%, even though the mean is 23%. What's the probability of getting over 40%? P gets used a lot here. I'm going to rewrite this as probability so it doesn't look like proportion. What's the probability of one sample? You should say that is a normal CDF question. My lower limit would be 0.4 because I said greater. How high do I need to go? Well, you can't be over 100%, you might think. Or you could say, well, the standard deviation is only 0.05. So if I went like 5 of those out there, but again, just pick some big number, 99, I don't know. The mean is 0.2308. The standard deviation is 0.0544. Normal CDF is going to tell me what that is. And I can see right here, I already know over here that this tail is about 2.5%. And I'm saying even to the right of that. So I better get a number less than 2.5% because 0.4 is even further past that. As a matter of fact, it's 7% past that. It's way out there. So I'm actually guessing, I'm guessing 0.4 is right there. No, that's actually not true because that's 0.339. That's only 1/1000th. So I didn't put that in the right spot. It's way closer to this line than I was thinking. No, it isn't. I'm right. That's 0.34. It is way over there. So we're going to get a really tiny answer for this. What's the magic machine say? Normal CDF. Lower limit 0.4, upper limit 99.2308 is my mean. Standard deviation 0.0544. Bam. Oh yeah, tiny number again. Scientific notation 0.0009. As I said, though, although that's a small chance, not very many samples of 60 cards are going to do that. Although that's a small percent, I'm not betting on that. If you have 5,000 trials, that's going to happen some. Let's finish with this then. If I go back to this screen over here, and can't see that very well, but notice that's 4,596 trials. So I'm taking that percentage in my calculator, it's still there. And I'm saying times 4,596. I got 4.2. Take a look at what this is saying over here. I happen to have exactly 40% here. And this is saying, when I multiply that out, I think I said 4 times. What's the probability of being above 40%? Notice I'm getting, there are numbers over there. As tiny as that possibility was, notice this is actually behaving in a sense, I guess, as you would have thought it would. Remember, if I hit restart, I'm going to get a totally different, it's still going to be normal like that, but I'm going to get a totally different answer. Do you agree in this particular sample that this one's lagging behind? You see how that's kind of not as normal as it should be? Should be a little taller, kind of maybe up in there. Well, like this one is. I'd say that side looks really good. Remember, this is still just a sample. So it's on its way to normal, but it's not perfect. Okay. The only thing I would say is the questions in the assignment are just like what we did here, and they're not bad at all. But remember, the important thing next week is going to be to say, what's the chance that your one study landed way out there when you don't know the right answer? Today, we knew the right answers to these questions. We were not surprised that 548 was the tallest bar because we mathematically knew what the probability should be. But in the real world, you're doing a study, you actually don't know the right answer. So you have to give a confidence interval. And we're going to be using the same idea. Do that next week. Stay after if you need to, or I will see you on the flip side.